Not long ago I published a video on YouTube about this Rose engine. This Rose engine was slightly different in that the cross table is driven by stepper motors, and I showed how you could move the cross table by stepper motors. An interesting exercise, but not particularly world shattering. I have now modified it in a way that I believe to be completely unique. We have the addition of a belt-driven encoder on the top. This allows information to be sent to two Arduinos that then translate this into a virtual rosette, and the cross table has now become CNC controlled, so that I no longer use physical rosettes. You'll see they've gone, but these are virtual rosettes, and the movement that you would get from a virtual rosette by rocking the headstock is now obtained by moving the cross table. The Z-axis is in use for on this occasion I'm using it as a laser. It could be used for a mini router. In fact, I have a mini router set up exactly for the center of the spindle. The router does work, but this is probably better used as a laser machine because the lack of it is not really rigid enough. You can produce decent results, but rigidity is the problem. Cross table is driven by two stepper motors. This one is the Y and this is the X axis. There are limit switches fitted but not in use yet. The electronics are contained within three boxes. The first one, this box contains the spindle controls, which allows the motor to run at various speeds, also to move in precise angles as you would an index setup, or you can move in steps, anything from 1 to 360 in a circle. So that's really quite handy. The other box, that's this one, sits on top of the main electronics, which house an Arduino Mega, the laser driver, a small 5-volt buck transformer, and an Arduino Uno that drives the laser. This is the second box, is really a Y-axis control. Has a DM542 laser stepper motor driver. The switches are, the one on the left is to arm the laser, the one in the middle turns the power off to the laser, the yellow button fires the laser, and the potentiometer control alters the power of the laser. As I've said before, lots of 3D printed parts. Most of the headstock is 3D printed. The encoder mounting is 3D printed. Parts of the spindle are 3D printed. The mounting for the mini router is 3D printed, as is the mounting for the X stepper motor and the mounting for the laser screen. All the boxes are 3D printed. In fact, I've had a real heyday with my 3D printer. It was the purchase of a brand new, quite fast 3D printer that made me start this malarkey. The next part of the video will show you the mechanism in action. Other bits. I have the eye protection from this, which actually is a small piece of filter, but it does work. rosettes are still on the machine, although I never use them, and the machine is locked in place by wedges down at the bottom. If I was going to redesign this thing from scratch, I'd probably put in a proper rigid headstock, although I've yet to find a way to do the spirograph control with electronics, so I still, if I want to produce a spirograph type pattern, I still need the rocking headstock. So to start the mechanism going, we turn on the spindle. It's running, and it's set for a sine wave rosette, a 6-point sine wave, and all I do is press rose go, and you can see the table moving to and fro. The nice thing about this is that I can change the rosettes anything up to 24 lobes. The amplitude can be changed, and I can do phasing without touching any mechanicals. It's all done electronically, which again I'll demonstrate a little later. Here the machine is set up to show you how the laser works and reproduces the electronic rosettes. Cross table is now going, and the laser is set up so that it will automatically turn off when the workpiece has turned 360 degrees. This helps to prevent overburn. You see, it's really quite bright. So you can't see what's going on at the face of the workpiece, but you can see the results. When it reaches where it started, the laser will turn off. Magic. I will now set the electronics to a 30-degree phase, and it will burn a phased pattern. Easy as that. How simple is that? Really quite good results with a laser. I'll now burn a pattern with more points. I cannot remember how many I set it for because I'm doing the voiceover sometime after I did this, but you can count them if you're interested. But it is really so simple to change the number of points on the rosette. Anything you can do with a laser, in theory, you can do with the mini router. It, as I said earlier on, it does produce acceptable results, but the main problem is the whole system could do with being a bit more rigid, which I will work on. Next I'll burn just a simple circle, again just to show you how the laser turns off automatically after a 360-degree turn. I can change that so that it can overburn if I want to. I could in fact, this laser is quite powerful, I could in fact I think cut through thin wood using it. Here's the electronics control panel. Z down, Z up lifts and lowers the laser. X left moves the table right, X right moves the table right, Y plus moves it forward, Y back moves it backwards. How much it moves can be changed by these buttons, so 1 centimeter, and it will now move 1 centimeter at a time. Laser on will turn the laser on at low power so that I can sight where I want to go. Laser off turns it off again. The next page is where the rosette works. Once the spindle is rotating, you engage the rosette by pressing rosette go. Rosette stop. I can change the number of lobes on the rosette by these buttons. Currently it's set for 6 lobes, but by increasing it I can have as many lobes as I want. Amplitude changes the amplitude. It's currently set for 10 millimeters, but again that can be set increased or reduced to change that. Phasing will allow it, this is the button I use for phasing, so I can increase that in 2.5 degree steps and reduce it similarly. Pattern gives me the different virtual rosettes. This is where you can see what they are and change the pattern back again. 360 or manual, this is where the laser will fire. When it's set for 360, will only fire for 360 degrees to avoid overburn. Put on manual, it will burn all the time. This is the laser arm button. Laser currently armed. Turn it again, laser safe. Armed, safe. And I actually fire the laser by pressing the yellow button on the box. Laser power will show here when I change the potentiometer, so it's currently set to 50%. It goes up in 10% steps. When I'm using the mini router, I need to be able to advance it from this page, so these two buttons here will move the X table in or out either by 1 millimeter or 0.1 millimeter. Back will take you back to the first page. The spindle is controlled by a separate box. Run, stop, angle, so I can set it to move 15 degrees. If I want to change that, it goes up and down. This is where the display is, so that it will only move 15 degrees at a time. Speed, using the plus and minus buttons here, is where I can vary the speed. It needs to go quite slowly for the router. Direction will change it from clockwise to anti-clockwise. Jog will move it a number of steps, so I can, using here, the circle is broken into 20 sections which I can increase or decrease, and it will jog portion of that circle. This is the button. Jog is where, this is where I set the value, and this is where it moves. The electronics inside the box, this is the spindle control box. It has a small Nextion 3.5-inch screen. The controls are run on a Arduino Mega, and that is a small buck power supply. Underneath that is a DM542 stepper motor driver. Inside the main control box for the CNC, we have a ramps shield sat on top of an Arduino Mega. This provides the controls for the X and Z axis. There's a separate DM542 in this box to control the Y axis. The demands seem to have been too heavy for the ramps controller, so that's why it's kept separate. The rat's nest of the electronics I apologize for. This is a Schmidt trigger chip. The encoder signal goes into that, where it's cleaned up and split between the laser and the Y-axis driver. Underneath that there is the laser driver and a small Arduino Uno which controls the laser. I've tried to clean up this rat's nest, and unfortunately that's the best I can do. I'm not proud of it, but it does work.
Here are some more examples of the kind of patterns I can produce electronically.
I'm setting this pattern for 24 lobes with 5mm amplitude, and I'm setting the laser to fire for 360 degrees. Laser on. Well, it would have done if I'd turned the rosette on, so we're getting a plain line. I will turn the rosette on as soon as this is finished. Hopefully you'll be able to see the laser turn itself off at 360 degrees. There we go. Now I'll turn the rosette on, and the laser goes on. Can't really see that because it's right on top of the line we've previously drawn, so what I'll do is move the laser when it's finished and try again. Okay, so stop the laser. Move it in 1 centimeter. There's that going, and press fire. Who needs physical rosettes when you can do it with electronics? Isn't that pretty? Fire. Do a slightly different pattern this time. Fire. This is a more pointy pattern. The thing about doing it this way is you get completely faithful reproductions of the rosette. And here it is. I've added the ability to pump this machine so that it can produce a pumping action. So this is another screen on the Nextion which commands a pump on, pump off, stroke, how long, whether you can increase the stroke or decrease the stroke, phasing, phase plus, phase minus, number of lobes, as in the ordinary side of things, and pattern plus, pattern minus. And then to be able to jog it to where I want it, I've got Y jog, Y plus, Y minus, X plus, X minus, home, which will take the carriage to where I want it to go, and then these are the jog values. 10 millimeters. It does work, but the processing demands on the ramp are such that the chip gets very hot very quickly.
If you check out the description, I have made available on GitHub a manual if you ever wanted to produce such a machine, and also the code will be available, the Arduino code that was developed by myself and using ChatGPT, without which I would never have been able to finish this project.